Students, welcome to the part 3. Now we are discussing another important value of alternating current, which is known as root mean squared or effective value of AC. It is also known by the name virtual value of AC. Its measurement is based upon the heating effect it produces when it passes through a resistance. We know that by the Joule's law of heating effect, H is equal to I square RT, where I is the direct current passing through a resistance. Now, because the heat produced is directly proportional to the square of the current, so it is not proportional to the current, but it is proportional to the square of the current. This means that when an AC current is also passed through the resistance, the amount of the heat produced, it will not depend upon the positive half cycle value or the negative half cycle value, but it will be proportional to the square of the both of the positive and negative half cycles, which will give after squaring both positive values. This means that if we have some AC current of say 2 ampere passing through a resistance, then the heat produced in the resistance for a small time t, it will be not proportional to 2, but it will be proportional to 4 value, that is square of the 2. So here in this figure, in order to measure the root mean squared value or the effective value of AC, what we have done, that we have squared the value of the alternating current so that even the negative half cycle is becoming positive after the squaring. So just like in case of average value, we divided the half cycle into the n intervals and we measured the average value over there. Here we are also dividing the total time interval for one full cycle of AC from 0 to t, from 0 to t time period into n equal intervals, such that at each interval the currents flowing through at different instant of time as I1 square, I2 square, I3 square, I4 square, I5 square or I square n. In this case, if we find out the average value of all these currents, it will be called as effective value or RMS value of the current, and we can write it as I square RMS. We are finding the average of the squared currents, so that's why we are writing I square RMS, which will be equal to I1 square plus I2 square plus so on up to IN square divided by number of intervals. So in this case, IRMS, it will be equal to I1 square plus I2 square plus so on up to IN square divided by n whole under the root. This is the RMS current by this basic definition. Now if this RMS current passes through a resistance for a small time t, which should be equal to the time period of the AC cycle, then heat produced in that resistance will be, according to Joule's law, H will be equal to I square RMS into resistance into the time t of the full AC cycle. We keep this equation as equation number 1. So because we have taken the average of the square of the currents, this means that this average is not going to change with the time, so we call this RMS current as the steady current or the DC current. So in this case, its definition is, it is that steady current which produces the same amount of heat in a given resistor in a given time as it is produced by a given AC when passed through the same resistor for the same time, that is equal to the one full AC cycle. So in this case, whether we are passing an AC current through a resistor equal to its own time period of AC cycle capital T, or if we pass this steady current IRMS through the same resistor for the same time capital T, in both the cases, then the heat produced will be same. Then we can say that this RMS value of the current IRMS is equal to in magnitude to that value of the AC. So in order to find the expression for RMS value of current, let an AC current I is equal to I naught sine omega t is passed through the resistance R, and when it is passed through the resistance R, it is able to produce heat in small time dt, which will be dH equal to I square R into dt. We want to find total heat produced in the time period t equal to the one full AC cycle. Then that heat H will be equal to integral of dH, which will be integral of I square R into dt from 0 to t. I is equal to I naught sine omega t. So if we substitute its value, we will have I naught square R into sine square omega t into dt. I naught square and R, they are constants, so can be taken outside the integral. I naught square R into integration of sine square omega t into dt, limit from 0 to t. Now, in order to evaluate this integral, we can write sine square theta as 1 minus cos 2 theta over 2. So we will have 1 minus cos 2 omega t over 2 into dt. So h will be equal to 2 can be taken out. So I naught square over 2 into integral of dt from 0 to t minus integral of cos 2 omega t dt from 0 to t, which will be equal to I naught square R over 2 into integral of dt is t, limit 0 to t, minus integral of cos 2 omega t for full cycle 0 to t. It will be 0. So we can directly write down its value as 0. So h will be equal to I naught square R over 2 into t minus 0, or h is equal to I naught square R over 2 into t. This is our equation number 2. Now if we compare equation 1 and equation 2, equation 1 has h equal to I square RMS t and h is equal to I naught square R by 2 into t. That means we can write, comparing, making them equal to each other, I square RMS R into t equal to I naught square R over 2 into t by 2. So here R get cancel and t get cancel. We get I square RMS is equal to I naught square over 2, or I RMS is equal to I naught over under root 2. So this is the relation between the RMS value and the peak value of the AC, which we can write also as 0.707 I naught, or 70.7% of I naught. So from here we get that effective value or virtual value or RMS value of AC is 70.7% of its peak value. If we do the same calculation for alternating EMF, we can also show that for alternating EMF its RMS value is E naught over root 2. Thank you.